The next talk is also about a great controversy, the Superluminal neutrino, an opera in 3 acts, and the speaker is Susan Cartwright.
My name is Susan Cartwright. I'm a neutrino physicist from Sheffield, and I'm going to talk to you about one of the more recent controversies in particle physics that John Butterworth kindly left out of his account of particle physics controversies this morning. And some of you may remember this. A few years ago, there was an announcement that by an experiment called OPERA, that neutrinos travel faster than the speed of light. So hence my title, Superluminal Neutrinos, an opera in 3 acts. And like all good operas, mine has an overture. In order to understand what is going on here, I'll need to tell you a little bit about the opera experiment itself and a little bit about neutrinos. So neutrinos are the most elusive particles of the Standard Model. You can think of them as very closely related to electrons, but they have no electric charge, they have very nearly no mass, and their usual response to anything else is to go straight through it. So if you were to take a look, for example, at your thumbnail, every second about 65 billion neutrinos from the sun are traveling through your thumbnail. Your thumb is not turning green or sprouting strange growths, because through is indeed the operative word. They go through your thumbnail and through the Earth and out the other side. And if you wanted to collect one specific neutrino from the sun, you would need a detector consisting of several light years of lead, which I don't frankly think the Science and Technology Facilities Council is going to pay for. But if you have a sufficiently intense neutrino beam, because interactions are a matter of probability, you have some probability that some small fraction of your neutrinos will indeed interact in your detector. And this was the principle of the OPERA experiment. The neutrinos were actually made at the CERN nuclear physics lab. In fact, as a byproduct of the proton rings that deliver the protons to the Large Hadron Collider. If you take that intense proton beam and you smash it into a target, you get pions, and pions decay after a few tens of nanoseconds to muons, which were mentioned by Michael, and neutrinos. And therefore, you can produce a beam of neutrinos which you can direct to your experiment. And in this particular case, they were directed 732 kilometers to an underground laboratory in Italy off the Gran Sasso road tunnel. You tend to put neutrino experiments underground or underwater or under ice in order to reduce the background from cosmic radiation coming in from above. And so this was a pre-existing facility, and the neutrino beam was directed towards it. The OPERA experiment itself was in fact designed to test the idea, now well established. It won the Nobel Prize for Kajita-san and Art McDonald in 2015, that neutrinos can actually change identity in flight, so that these neutrinos, which start off being related to the muon, can be detected as neutrinos that are related to one of the other 2 charged leptons, the electron or the tau. And so the idea of OPERA was to look for evidence for the production of tau leptons by doing very sensitive studies of the decay of this produced particle. The tau lepton is a very short-lived particle. It decays after a few millionths of a second, so you need this very, very finely grained detector to detect it. So the neutrino velocity was a byproduct. I think, in fact, it was some student's PhD thesis. And the idea was, because these neutrinos had quite large energies, and because neutrinos are very, very nearly massless, they are at most 4/millionths of the mass of an electron, and an electron is only about 1/2000th of the mass of a hydrogen atom, so we are talking about something with a very minute mass. And so it was expected that these particles would travel at essentially the speed of light. So the speed of light is a special thing in relativity. Anything that is massless travels at the speed of light. Anything which has a non-zero mass must travel more slowly than the speed of light. And this is essentially a consequence of Einstein's special theory of relativity. And the equation E equals mc squared, strictly speaking, is only true for mass at rest. If we have our mass moving, that equation can be written as E equals gamma mc squared, where gamma squared is the speed of light squared divided by the difference between the speed of light squared and the square of the velocity of the particle. And you can see that if the velocity ever gets to c, you're in trouble because that has become a divide by zero. And the only way in which that equation doesn't blow up is if the mass is also zero, in which case you get 0 divided by 0, which is mathematically undefined, and you have to look at a slightly different formulation of this equation to find out what the energy is in that case. If the velocity is greater than the speed of light, you have an even more problematic situation, because gamma is then the square root of a negative number. Those of you who remember your A-level mathematics will know that the square root of a negative number is technically referred to as an imaginary number, because in the real numbers this does not exist. If you take a negative number and square it, you get a positive number. And so the only way in which the energy, if you have that being the square root of a negative number, can be a real number, measurable quantity, is if the mass is also the square root of a negative number, in which case the two minus signs will cancel out and you wind up with gamma squared m squared being respectively positive. So one of the problems of having things traveling faster than light is that it implies that they have masses which are not real numbers. The other problem with velocities greater than the speed of light is that if something travels faster than the speed of light, then it is possible for an observer moving with a different velocity to see it arrive at its destination before it left. The transformations of special relativity can give you a negative time. And this is often described in textbooks by the light cone. If you are sitting here in the middle and you regard time as going vertically and you condense space down to 2 dimensions like so, anything inside this cone is the paths of light rays that either arrive at you or are emitted by you. Anything inside that cone, which is going slower than the speed of light, if it's in your past, it can have affected you. If it's in your future, you can affect it. And whatever velocity of the velocity of an observer, they will always see those events occur in the same order. Anything outside that light cone, depending on the observer, the order of an event outside the light cone and you can be inverted. So causality does not hold if things go faster than the speed of light. So people tend to frown on things that go faster than the speed of light. We scientists tend to believe in cause and effect. So that completes my overture. Act 1, the signal. Opera calculated the velocity of their neutrinos in the most simple-minded fashion possible. You know the distance between where your neutrinos were created and where they are discovered. You measure the time it takes them to get there. You get the speed by dividing the distance by the time. This is a perfectly straightforward idea in principle. And they used GPS to get their times in what is called common view mode. In other words, they ensured that both their receivers were talking to the same satellite, and that gives you a more accurate time difference than ordinary GPS. The trouble is that that may be conceptually simple. In practice, it is not simple. These are diagrams from their paper. I do not propose to go through them in detail. You will be delighted to hear. The point is that it takes time for the proton beam to be converted into a neutrino beam. There are various electronic devices that introduce delays. You know what those delays are, but they are big. This one, for example, is 10,085 nanoseconds, but you know it to a precision of plus or minus 2. So it's complicated. It is not just a simple case of take clock signal from here, take clock signal from there, subtract them. It's a lot more complicated than that. And that was the CERN end. This is the Gran Sasso end. You will obviously have noticed that GPS signals do not work underground. And so the GPS signal has to be picked up outside the tunnel and then transported into the tunnel by a fiber optic cable, which again produces an enormous delay, 41,000 nanoseconds, which they knew to a precision of plus or minus 1. So there are many delays, and the time difference you measure is in no way the actual time difference of the neutrino travel time, and you have to correct for all these delays before you actually know the answer that you've got. And so, in actual fact, they did something which was quite clever, and that is that they left their reference time as what it had been in 2006. And in actual fact, they knew that that had changed because there had been a small earthquake in Italy in between 2006 and 2011 when this measurement was made, and they knew it had slightly changed the distance between the start point and the end point, so they knew that that reference time was not right, but they left it there in order that it would not be obvious to the people doing the calculation what the right answer ought to be. And this is good practice. This is what doctors do when they hold blinded clinical trials. The doctors don't know whether their patient is getting the drug or the placebo because that avoids unconscious bias towards getting the right answer. And so they did that, and that was good scientific practice. And what they found was that to shift the observed signal to the reference, they had to shift by 1,048.5 plus or minus 6.9 nanoseconds. And then they, as the saying goes, opened the box to find out what the answer should have been, and the calculated shift was 987.8 nanoseconds. And that, because the shift is backwards, meant that the neutrinos had actually arrived before they should have done, by an amount 60.7 plus or minus 6.9, and a systematic error caused by all these corrections of plus or minus 7.4. If you combine those errors according to the prescription, as if they were part of a right-angled triangle, so you take the squares, add the squares, and then take the square root, this comes out as a 6 sigma effect, so it is well beyond the 5 sigma particle physics discovery threshold. And what it implies is that the speed of the neutrinos in units of the speed of light differs from 1 by 2.5 parts in 100,000. So it's not a big shift, not a big effect. But it is an effect that is well beyond what we claim to be discovery threshold. At this point, they actually decided to go public. They published a preprint, and I was sitting minding my own business in my office at Sheffield. I'd just come back from giving a first-year astro lecture. My mind was thoroughly on elementary stellar evolution theory, and I got a phone call saying, Hello, is that Dr. Cartwright? Yes. This is the science correspondent of The Guardian. What do you think about Opera's result on superluminal neutrinos? I'd been teaching all day, I'd never heard of it. I was standing there going, well, you know, neutrino experiments are quite difficult, and there may be systematic errors that they haven't thought of, while frantically Googling with the other hand, Opera superluminal neutrino. So this is basically the signal. And the key point is that, according to Opera's calculations of their errors, this is highly significant and absolutely passes the publication threshold. So they therefore wrote a paper. And then this concludes Act 1, and we now move on to Act 2. They wrote their paper. What happened? Well, famously, Jim Al-Khalili said that if this result is right, I will eat my boxer shorts on live TV. I actually gave a talk in our department because after the 6th person asked me this question, I thought, look, I'll give a seminar. That way they will all know what I think about this result. And what I said, and I checked my PowerPoint slides, which I still have, and which I plagiarized when writing this talk, and what I said was, if there is a simple error, my guess is that it's in the timing corrections, which are difficult to check without crawling all over the equipment. So, what did other people think? Well, by and large, there was some evidence, rather ambivalent, but tending to support it. There was an experiment which had previously been made by the Minos experiment in America. It's another neutrino experiment. It had essentially an identical beamline, 2 kilometers different, had a lower energy beam, had standard GPS timing, so looking at different satellites, so not as accurate. And they had done this measurement before, and they had got a result which was ambiguous. It is not 0, technically. The error bar excludes the central value is not within 1 error bar of 0, but it's within 2 error bars of 0. This means that about 1 time in 15, if you do a measurement like that, you expect to get a result that's that far from 0, even if it actually is 0. And as John said, we particle physicists make hundreds of plots every year. You expect 1 or 2 of them to come up with 1% errors. So Minos published this result, but they did not claim a positive detection. They used that result to set an upper limit on how much faster than light neutrinos could be going. A key point is that there, at which you also saw in Opera, was that there was no distortion either of the energy spectrum or of the time structure. So there was no evidence of any energy dependence in the time of flight of the neutrinos. And this is a problem because in 1987 there was famously a supernova in the Large Magellanic Cloud. The Large Magellanic Cloud is 156,000 light years from here, and it's every extragalactic astronomer's favorite calibration source. There are dozens, literally, of distance measurements to this object. We know that distance to within plus or minus 3%. And again, famously, neutrinos were observed by 2 experiments which were actually designed to look for proton decay, but discovered that they could detect neutrinos as well. Kamiokande and the Irvine, Michigan Brookhaven experiment, IMB. This is the Neutrino Spectrum. So over about 10 seconds, there were a couple of dozen neutrinos detected from this exploding star. Now, the key point here is that light takes 156,000 years to get from there to here. So that supernova didn't go off 30 years ago, it went off 156,030 years ago. The timeline of this detection is very well known. This was a star which had previously been catalogued. It's called Sanduliak -69202. And on the 2:20 in the morning on the 23rd of February 1987, it was still there at magnitude 12, just like it had always been ever since Sanduliak catalogued the thing. 5 hours later, the IMB neutrinos were detected. We know when the IMB neutrinos arrived because they had a GPS timestamp on their events. Kamiokande did not, because they didn't think it was important to know exactly when a proton decayed, so they were just relying on their computer clock, which in those days, before everything in the world being connected to GPS, was about as accurate as a clock on the wall. So they were at a similar time, but we can't tell when they were at to the nearest second, just to the nearest couple of minutes. 3 hours after that, a photographic plate was taken by McNaught, which when subsequently developed, showed Sanduliak minus 69202 at visual magnitude 6.5. That means it had increased in brightness by a factor of a couple of hundred between 2:20 and 10:38. So the explosion happened somewhere in between these times, and it was actually discovered at 5:31 by Ian Shelton, 5:31 on the 24th by Ian Shelton, and by that time it was naked eye visible. I think it's the only astronomical discovery in modern times where they checked by going out of the observatory and having a look. Now, the neutrinos, even if as soon as that plate had been taken, it blew up, the neutrinos arrived not more than 5 hours after the light and not more than 3 hours before the light. So that means that at most, the difference, the fractional difference in speed was 2 times 10 to the minus 9, not 2 times 10 to the minus 5. And in fact, we expect the neutrinos to get out before the light, because neutrinos get through stuff that stops light. So the light has to fight its way out from the collapsing core of the star, and it takes it a few hours to do so. It would have been more than 3 hours, but Sanduliak minus 69202 was a blue supergiant, not a red supergiant, which is a nice compact object, so the light went out quite fast. If the neutrinos had been traveling at the same speed that Opera said that their neutrinos were traveling at, they'd have arrived 4 years before the light. There's a difference between 4 years and 3 hours, which it doesn't take GPS timestamps to recognize. So the community response, experimental physicists like me and like Alphonse there, generally speaking, did not believe a word of it. To quote, I think, Carl Sagan, extraordinary claims require extraordinary evidence. 6 sigma or no 6 sigma, we were having none of it. Most theoretical particle physicists provided interpretations assuming that it was true. It must be fair. What must be fair? This does not necessarily mean that they genuinely thought it was. It necessarily means that they genuinely thought they could get a paper out of it. The theoretical responses were varied. Cohen and Glashow, that's Sheldon Glashow, the winner of the Nobel Prize, the co-winner of the Nobel Prize for the weak interaction, took the firm view, it's wrong and we think we can prove it. There were other people, such as Micozzi and Bellini, who said it may be right, but we can understand it in terms of known physics. Then there were the people who leapt with great enthusiasm on the bandwagon. Ever since supersymmetry declared that our universe has 10 or 11, string theory declared that our universe has 10 or 11 space dimensions, there is a general belief that whatever is wrong, it's the extra dimensions what done it. And there were various people who claimed that. And there were also various people who claimed that it was some mysterious new interaction. So there were many theory papers. It was very difficult to get this to work with the constraints provided both by the results of these neutrino flavor-changing experiments, which also set constraints on the mass differences, and the supernova. If you allow sensible energy dependence, such as a power law, then you find that the opera signal is here in red, and the allowed region constrained by supernova 1987A, neutrino oscillations and various other things, is the shaded blue region, which is nowhere near the red region. You can get regions in which you can get it into an allowed region, but it requires you to make ad hoc assumptions about the energy dependence of this effect. This says hyperbolic tangent dependence. Now, a hyperbolic tangent dependence goes, it's basically a step. So essentially, you switch it off for the supernova and switch it on for opera. That I regard as, well, I have written here, a bit contrived. The experimental community, despite the general view that it was a load of tosh, did nonetheless make the correct response, which is to try to replicate the results. As Michael said last time, one experiment is not evidence for anything because one experiment can always be wrong. But to accommodate the supernova data, your effect has to be very, very energy dependent in some weird and not very well understood way. So ideally, you need to replicate it in the same beam. Fortunately, this could be done. There was another experiment at the Laboratoire National Gran Sasso, Icarus, which promptly started measuring time delays with great haste. And CERN set up a special run designed for precise timing where the neutrino bunch was shorter and had sharper edges. So, how was this resolved? Well, here's Icarus. They got a time difference of 0.3 plus or minus 4.9 plus or minus 9. This is nowhere near Opera's. That number is slightly different from the number I quoted earlier because that number comes from version 2 of their preprint rather than version 1. But in any case, there is no overlap here. Icarus were confident that the neutrinos they saw had traveled at the speed of light, no more, no less. Meanwhile, back at Opera, obviously something has to be done. So they started frantically checking their time corrections. As I said, crawling all over the experiment. And one of the things they did was to remeasure the time delay in their fiber optic cable. So, in 2006, it was 40,990.5.5 plus or minus 0.3 nanoseconds. In December 2011, it was 41,068.6 plus or minus 0.5. You will notice the difference there. Looks suspiciously like 60 nanoseconds. They plugged it out. They took it out and plugged it in. It went back to 40,995. The signal was a loose connection in the fiber optic cable. Much embarrassment was had by all. So, going back to our previous comments, Jim's underwear is safe, and I told you so. I was feeling quite smug for quite some time after that announcement. So, coming to our topic, physics controversies. First question is, should Opera have published their original result, given that it does turn out to be a simple error in the timing corrections? The fiber optic cable is the single largest time delay, and so perhaps you could argue that it's the single most obvious potential source of error. Maybe they should have checked it before writing the paper. This seems obvious in hindsight. Hindsight is a wonderful thing. You do not instantly assume when if your television suddenly stops operating, that the plug has fallen out. They generally don't. Nobody had touched that fiber optic cable as far as Opera knew. There was no reason to believe there was anything wrong. And although that was the biggest time delay, many of the time delays were bigger than the travel time, so one could not argue that that was the only one that could possibly be at fault, and there was no way they could check every time delay. And furthermore, taking the fiber optic cable out would have involved stopping data taking, and remember, this was a byproduct. This was not their principal physics goal. So I think it's probably fair to say that with hindsight, yes, of course you'd have checked everything. At the time, there were rumours going round. It was probably better to publish and be damned than to hang about waiting for the next shutdown so that you can check all the timing corrections. Was the community response appropriate? Well, actually, I think we come out of this one pretty well. Although everybody in the experimental community thought it was rubbish, attempts to replicate it began immediately. CERN provided facilities for improved precision. Using those facilities, both experiments got results consistent with zero. I think the theorists were right to take it seriously. They were not in a good position to check whether it was valid or not. If it had been right, then it would have required a total rewrite of a large number of laws of physics, and therefore the more ideas on the table, the better. And at worst, which is what happened from their point of view, they end up with a paper that they probably don't quote when asked to give their list of publications. So it's a no-lose situation, really. If you're right, it wins you a Nobel Prize. If it's wrong, you quietly sweep it under the carpet. So, for my conclusion, I'm going to quote the conclusion of a review article by Alan Franklin, which says, "The consensus is that it does not exist. The discord has been resolved by a combination of finding errors in one set of experiments and a preponderance of evidence." A fair summary, would you agree? That is not about the opera result. That is from a 1995 paper entitled "The Appearance and Disappearance of the 17 keV neutrino," which some people here in Oxford may know a lot more about than I do. This was a result in a neutrino oscillation experiment which claimed that there was a new type of neutrino at a mass of 17 keV, and which turned out, as the quote says, to be due to a failure to understand all their experimental systematics, and which was not replicated by experiments that used other methods. So we have been here before. Operas was not the first incorrect result to be published, not even the first incorrect result to be published in particle physics. And I am willing to bet large sums of money that it will not be the last incorrect result that finds its way into the scientific literature. And to quote Stephen Jay Gould, one of his essays, "Good science is self-correcting." But one has to say, good science is self-correcting eventually. It may take quite some time. Thank you.
Thank you, Susan, for the really great talk. But I have to ask you a question. Do you remember the seminar at CERN from Antonio Ereditato, the head of opera? Was that before the preprint came out, or?
I think it coincided.
Coincided with the paper.
Yeah, same day.
Same day. So weren't they are looking for publicity as well in some respect?
Yes. But it was a CERN seminar, it was not a press conference. They are slightly different.
Okay, questions?
Quick question. For neutrinos that generally aren't stopped by even the Earth, how do you collimate a beam of them?
By conservation of momentum. Your protons smash into your target at high speed, the pions share that momentum, and the neutrinos from the pion decay. It's not a well-collimated beam, it's a broad fan, yeah. But it is all heading more or less the same direction.
Obviously, thank you. Yeah.
Thank you for an interesting, entertaining and informative talk. Do you think if the neutrinos had been seen to be coming slightly slower than the speed of light, there would have been the same haste to repeat the measurements?
That's a very good question. I think the answer is probably yes, because if they were travelling slower than the speed of light, the natural interpretation of that is that they have a mass which is much larger than we anticipated. And that would be very important, particularly for cosmology, because neutrinos are what cosmologists call hot dark matter. and they strongly affect the evolution of structure in the universe. So I think it might not have been quite so all-embracing. Every neutrino experiment decided it would do a neutrino velocity measurement, but I think there would have been a rapid response to a significantly slower than light measurement as well.
This is really a comment in defence of theorists. If it did nothing else, it produced the best abstract of all time. This is Mike Berry's paper, and I just was checking it on the archive. So Berry, Brunner, Propesco and Schuckler. The title was, Can Apparent Superluminal Speed be Explained as a Quantum Weak Measurement? And the abstract was, Probably not.
Very nice. More questions?
Oh, hi. A couple of questions. So what happened to opera and the people involved afterwards and their reputation? And the second dumb question is, if neutrinos are massless, how do you measure them? How do you measure if they're there or not?
The first question is that the then spokesman of opera very rapidly became the ex-spokesman of opera. Second, can you repeat the second question, please? I didn't quite catch it.
How do you detect neutrinos?
How do you detect neutrinos? You do not detect neutrinos directly. There are two principal ways you detect them. One is that they can interact by the weak interaction and convert into the equivalent charged particles. So our muon-type neutrinos can convert back into muons, electron-type neutrinos can convert back into electrons, and that's how we detect them in the experiment I'm involved in Japan. The other thing that they can do is cause a response in whatever they hit. So, for example, the Chlorine Experiment, which was the first experiment to detect solar neutrinos, a chlorine atom, a chlorine-37 atom specifically, can capture a neutrino, convert thereby one of its neutrons into a proton, an electron is spat out, and you get argon, an argon-37 atom, which, being a noble gas, detaches itself from the compound, and you can flush those argon atoms out later. They are a radioactive isotope of argon, and you detect the radioactivity. So you can either detect the conversion of the neutrino into a charged particle, or you can detect the reaction in whatever it struck.
Is there a consistent time delay in these two particular events that you just described?
No, they are, well, yes and no. There is no time delay in the conversion of the neutrino into a muon. There is, of course, some time delay involved in the detection of that particle because it has to travel some distance before you actually notice it's there. The radiochemical detection, there is no delay in the conversion of the atom, but there is a large delay in your detection. And in fact, one of the difficulties with radiochemical experiments is that you are not sensitive to small time differences because you typically can only do a measurement every month or so, and you're integrating over that previous month.
I'm interested in the politics of this. I feel quite sorry for those who felt they had to resign, because I seem to remember in the original paper that they sort of said, we don't really believe this ourselves, but we've scratched our heads and tried everything, and we're appealing to the physics community to come up with some ideas to explain it, rather than asserting they had found superluminal neutrinos.
That is absolutely right. I think they fell slightly foul of the fact that it turned out to be such a simple mistake. As I said, hindsight is a wonderful thing. I don't believe it was in the least bit obvious to the opera collaboration that fibre optic cable was likely to be the guilty party. But when they found it was simply a loose connection, basically they became a laughing stock, and some head had to roll, and Ereditato was the unfortunate guy in the fire.
They didn't do every check, I mean.
Yeah, but I think... So it's kind of directly related. I was going to ask this before, because I think it's important to point out, I think it's true, you can tell me if I'm wrong,
But I think, I mean, he lost his role as spokesperson, but he did not lose his job. And I think,
No, he didn't.
So he didn't get fired. He just no longer was spokesperson.
Absolutely.
And I think that's when you say that the community came out of it well and that it was an honest mistake and that science is self-correcting. I think that's an important point to make. It's clearly reputational damage, and exactly as you say, it was a bit of a laughing stock because it was that kind of mistake. But he didn't actually get fired. He just stepped
He
back.
certainly did not. In fact, the week after this was resolved, I was on shift with him at TTK.
Yeah. Just in that context, I think in the experiment, he didn't lose his job because he had a wrong result. I think one of it was also how it was handled before in the experiment, because the experiment as a whole wasn't actually, so the collaborators were not aware of the result. It was kept secret within the experiment because they thought they were onto something big. And so internally the result was actually not scrutinized by the physicists, only in a very late stage. Many people did not sign the paper or the paper draft that came out, and it took some time for everybody to get on board and double check the results. So strategically or on how you organize your experiments, mistakes have been made, and I think in that context it was the right decision that he had to resign. That the result was wrong, for me, never played an important role in that
The
decision.
experiment's own procedures were not followed. Yes.
A lot of questions here. First on the back and then we'll come back to you.
Thank you. That was a very stimulating talk. I wanted to try and sort of connect this morning's discussions with the afternoon. It seemed to me in the morning the controversies were often triggered by issues external to the scientific community of the time, and so they may be religious or political, or in the case of the perpetual motion, are often fraudsters. Whereas the two talks this afternoon were about controversies within the scientific community. And so I was wondering what your views on whether it's getting harder and harder to do good science.
I think that is a fair comment, that this was very much, although there were many headlines about it, Guardian correspondent being a case in point, that it did play out largely within the scientific community and did not have much in the way of political repercussions. I mean, that when it was proved to be wrong, nobody threatened not to pay their CERN subscription, and nobody threatened to close Gran Sasso or set opera on fire or anything like that. I think what is true is that these days good science is often a difficult and collaborative endeavour, that it is difficult now to think of simple experiments that can test fundamental, what we think of as fundamental laws of physics, because the simple tests have all been done. So the test that gravitational waves carry away energy from close binaries was done in the 1970s with the Hulse-Taylor pulsar and its orbital decay, but to detect gravitational waves directly, dot the I's and cross the T's, you need LIGO. And LIGO is not cheap and not easy. And it is very difficult nowadays to be the lone crusader, rewriting the laws of science. The lone maverick genius slaving away in a Swiss patent office it's very difficult to sustain these days. So to that extent, I think it's got harder to do science outside the mainstream just because the resources involved tend to be enormous.
Perhaps you could just clarify one point for me about the delay. You seem to have one delay for the fibre dated 2006, then another one in 2011, and these were different.
Yes.
Did that not cause some eyebrows to raise
It
much
would have
earlier?
if that measurement had been made before rather than after the publication of the result. That was in fact the problem, but it was only found when they went and as I had said what they would have to do, crawled all over the experiment, checking every last time delay, and one of the ones they checked was the fibre optic cable.
Okay, but I've just there's one result in December 2011.
Yes.
Now I've forgotten the chronology. Here.
The Opera result came out in September 2011. So the December result, as I say, was a direct consequence of needing to double check.
But then there was another one afterwards that showed the same result.
Yes, that was after they had said, ooh, something is wrong here. We will do what you always do when something is wrong, which is turn it off and then turn it back on again, or in the case of the cable, take it out and plug it back in again.
Yes, but so the December 2011 measurement was made after the publication, etc. And then they started getting worried.
Yes.
Okay, thank you.
More questions for Susan? Oh, yeah, over there.
Hello. Thank you again for a very engaging talk, and I'd like to say I think the University of Sheffield are very lucky to have you, actually. Is this just not a case of the pressure that academics and researchers are always under to knock out papers, and if there wasn't that pressure, probably borne by the need to secure research, that this actually may never have happened, or do you think that that really doesn't have anything to do with it?
I think not this one, because the result, had it been right, would have been so earth-shattering. I think in this one, the only question is whether, had they followed their own internal review procedures, as Alphonse was saying, they would have made the fibre delay measurement before they put the preprint out, rather than slightly embarrassingly 3 months after. But I think this one is one that would have been published anyway. But I do agree with you that some of the results that get published that are of marginal significance are definitely caused by the need to stack up those publications because of external pressures. So it is a very good point.
Thank you very much.
He asked, is there another flavour of neutrinos to find? And the answer is, we know that there are 3, one for each of the charged leptons. There are some hints that there are 4, which come very much into the category of pathological science that Michael was referring to, that Irving Langmuir defined. They are small signals in experiments that have significant systematic errors, and they are difficult to reproduce. And there is, in fact, but this would have to be a neutrino which did not feel even the weak interaction. So an incredibly difficult thing to detect. The only way you can detect it is if the neutrinos we can detect turn into it during flight and therefore disappear from our ken, so to speak. And there is an experiment at Fermilab which is being set up even as we speak, which actually involves the Icarus experiment, which has been transported from Gran Sasso to Fermilab to take part in this, and that will hopefully definitively confirm or refute these signals. My money is all on refute.
But it would definitely be one or the other.
But it should be one or the other. I'm not holding my breath, because we have had another experiment whose tagline was that they would definitely confirm or refute the original result, and they did neither. As it happened, they came up with their own anomaly, which was somewhat different from the one that they'd been intended to test. So you can never trust these things, but it should produce a definitive answer within a couple of years from now.
And we are going to have 3 of them trying to see these oscillations, so it could be...
Yeah, Sheffield's involved in the...
It's SPND, yeah.
Thank you.